Now, last week's assignment looked really, really good. So the one that I just, the one you guys turned in last week. So that means this week we don't have an assignment or past sessions. Mhm. Yeah, so this week, we won't have, so there was no assignment that went up on Friday. And we won't have, and I've already talked to Ivy and she was like, I could really use the week off. I was like, yeah, let's just do that.
Great week already.
What, do you have no exams this week?
No.
Yeah. Weren't you supposed to take it this semester? You might want to do that. Mm-hmm.
So I'm trying to figure out how I'm going to do this.
Well, what's it called if I compress waves and they go from red to blue? What is that? If I compress light waves and they go from red to blue, what's that called? No, it has a specific name. Nope, it has a specific name. It's on the MCAT. So, because you need to study, figure it out. Okay, we'll do that too. But okay, so we're looking at this system of resistors in series. Now we started some of this, but we'll go through it again. Okay, so again, resistors in series and capacitors in parallel are, we like those. Resistors in parallel, capacitors in series, it's a little more annoying, but yeah, that's it. Nope, that's right. If you go the other way, if you stretch waves out, they go from blue to red. Uh-huh. Mm-hmm. Yeah, that's what it is. It's blue shifting and red shifting. Who do you have a chat with? Oh. May I suggest you actually study? I'm just a little concerned about the way things are going. In another class of mine, I had someone write on their homework, they wrote down the answer and they on right next to it, they goes, I looked this up on the internet. Do people even have a definition of what cheating is anymore? Because it's like looking stuff up, that's not someone actually doing the work. Well, I looked it up. No, it's not. You copied it. We need to make sure we understand our definitions of cheating. So no, that's not, you're not answering that for an assignment or an exam. No, I said you shouldn't use chat because it's wrong more than some of the others. You can use AI as a tool, but you have to translate what the AI gives you into only the theory we use in class or that's in the textbook. You have to translate it into proper derivations. You have to translate it into, you're limited. You can't just use anything that AI gives you. No, not even close. It was like last year, I had questions on on like, it was like an osmotic pressure question. And people were giving me these solutions involving like chemical activities and stuff like that. And I'm like, no, no, we're not doing that. It's like, and I actually had someone go, how'd you know that I got that somewhere else? I go, because the solution you gave me was a partial solution of something more difficult from physical chemistry, and you haven't done that. I know the whole solution. You didn't give me the whole solution. So, ergo, you copied it from somewhere. Just be careful about how you're using these things. These are supposed to be tools. Like I said, make sure you're doing things for yourself. Make sure you're, yeah, because you need to make sure you can still do the work. You need to make sure, like, maybe not in here, but across the country, literacy rates are declining. Like, it's bad. Yep. Depends on what you were reading. If you were reading Plato's Republic, there's an argument to be made. If you were reading smut, then yes. Okay, but still, but still. So there's an argument to be made. Depends on what you were reading. Not really. I guess it depends on the type of novel it is. Because, like, for example, if you're reading Tolkien, it can expand your vocabulary. If, perhaps, but so again, it depends on what you're reading. So we're looking at this series of resistors. Part A says, what's the equivalent resistance of the circuit? Well, since these are resistors in series, this one's super straightforward. So we get 18 ohms as the equivalent resistance. And then remember, you can redraw these circuits to help you kind of understand what you just did. So what you've done here, you've taken all four of those resistors. You've turned it into a single circuit. So what this is, and again, our battery is 6 volts. So the equivalent resistance is like taking all of those and turning them into a single resistor. Kind of important to remember this setup because we're going to do some problems where you're going to have to condense a circuit and then expand it back out to figure out the answer. So part B, the current in the circuit, if the terminal voltage of the battery is 6 volts, so there's that. So what's the current of the circuit? So seeing as how those are all in series, they're all going to have the same current. So we can just use, if we want the total anything of a circuit, we can use the equivalent. So the equivalent capacitor, the equivalent resistance. So in this case, our equation is I'll give you an example of some. Okay, I'll give you an example of something you can read that you probably haven't. On my chemistry exam, I put a phrase, abandon all hope, ye who enter here. Where's it from? It? Bravo. Yeah, most of my class told me it was from Pirates of the Caribbean. And when I said, no, it was from Dante's Inferno, someone goes, oh, I haven't seen that one. I go, no, Dante's Inferno, as in the Divine Comedy, as Inferno, Purgatorio, Paradiso. You what? Uh-huh. Also, I suggest reading 1984 if you get a chance. Mhm. For those of you who claim to stand against totalitarianism, 1984 would be a great one to read. Dante's Inferno. It's an epic poem. I guess not. Also, for example, To Kill a Mockingbird has been banned in high schools now because it says a certain word. The problem with that is it was supposed to be 1920s America, where sadly that word was still common parlance, but it's one of the very first anti-racism novels ever written. No, I think that one's worth reading. Lord of the Flies is also one worth reading. Yep, that's also. Yeah, that's a good one. No. Have you ever read Where the Red Fern Grows? That one will destroy you. That one will destroy you. So I'm saying there are things worth reading. Yeah. So like when I walk around and I see someone with A Court of Thorns and Roses, I'm like, that's no. First off, not worth your time. Second off, I now know way too much about you. Either way, either way, you're telling people too much about you. Okay. As long as you're studying for one of them, you shouldn't feel guilty. And you need to learn to balance your time. You hyper focus. So part C, calculate the electric potential at point A if the potential at the positive terminal is 6 volts. Okay, so how do you think we would do that? So to find the potential, so how do we label potential? Electric potential. How do we label it? Delta, no, that's potential energy. Yeah, Poe is for, I mean, Poe's okay, but that's more for like goths or whatnot, but it's, but yeah. What? No, that's potential energy. Potential. Delta V. So we're looking for delta V. And the reason I ask is because we want to know the delta V at point A, which means we have to know the voltage drop across the 2 ohm resistor. Okay. So that voltage drop so we now know our current 0.33 amps, 2 ohm resistor, we get a voltage drop of 0.66 volts. Now, you've seen the textbook call this a voltage drop. This is why it's called a voltage drop, because now the potential at A is going to be our the voltage of our battery, our electromotive force, minus the voltage drop. So that's the potential at point A after you've crossed that first resistor. And so if you wanted a point between any of the resistors, you just do this sequentially and you subtract off the voltage drop across each resistor. All right, part D. Suppose the open circuit voltage or EMF is 6.2 volts. Calculate the battery's internal resistance. Well, what equation do I use there? Kind of. What is the delta V equation that incorporates internal resistance? Yeah, what is it? And this will show you why a lot of the time we use delta V for the battery instead of the script E. Because in reality, your batteries are going to have an electromotive force and an internal resistance. That's going to actually make the terminal voltage less than the EMF. Yep. Okay. So we solve for R. And so in this case, your delta V is your terminal voltage. 6.2 amps minus 6 amps. Oh, wait, hang on. Those are volts. Volts minus 6 volts over the current, internal resistance, 0.6 ohms. Kind of, it's kind of like the Captain Crunch hat. Well, try to draw the symbol for so try to draw the symbol for conductance. That one was, I guess, where some scientists had a sense of humor. And so ohms is resistance, mhos is conductance, and it's that omega upside down.
What? The omega upside down?
Mm-hmm.
It's like making why.
I don't know, might not be. If you don't like drawing the omega, I doubt you'll enjoy drawing the upside down one. Yep. Just depends on which way your horseshoe faces. No. Just letting you know it exists. Okay. Resistors in parallel. Okay, so now you see, you're getting the idea that your capacitance and resistance equations are like the reverse of each other. Because you remember your capacitance in parallel was your equivalent C is just add all the capacitance together. This one is your 1 over Req, whereas your capacitors in series was 1 over CEQ. So they're like the reverse of each other.
Now, why am I so to already do that sum?
It has to do with the equations that relate them. So like you have to know where your delta V's are the same. You have to know where your Q's are the same. Look at the various equations. How does Q relate to capacitance? How does Q relate to resistance? And you start to see you're going to get inverses of each other. So again, well, but if you look, so what's one thing we know about circuit components in parallel? They all have the same what? No current, that's series. Nope. Same charge is for series. What do parallel circuit components have? It's the same what? Nope, that's series. Voltage, same delta V. So the first thing we know okay. So if they all have the same delta V, that's going to be I1, R1. So all of those equal each other. So that means I1 is delta V over R1. I2 delta V over R2. I3 delta V over I3. No, R3. All right. And now we know that our total current will be delta V over R1 over R2 over R3. Now, the left side is total current. And what can we use to find total current? So our what? So for the total current in the system, what resistance can we use? EQ. So this is going to give us delta V over REQ. Now, they all have the same delta V, so you can divide that out. How much room did I think I was gonna need? All right, well, here's our equivalent resistor, so we end up with and so you can just keep going for the same number of resistors that you have. Delta V. Capacitors in parallel also have the same delta V. You just have different equations relating delta V to capacitance and resistance. So again, anytime you have a circuit where you get an equivalent capacitor or resistor, you can reduce them down into a single resistor or capacitor which, to try to help them diagram what's going on. All right, let's look at this circuit here. You have the three resistors, potential difference of 18 volts. Find the, so if you ever see a mock-up that says so many volts connecting point A and point B, sometimes you'll just see a diagram where you see point A, you see the circuit element, and then you'll see point B. If they tell you that a voltage is maintained between those two, just hook them to a battery. And that battery will have the 18 volts that is maintained between those 2 points. So that's what they're telling you. If you ever see a circuit diagram without a battery and they're telling you to maintain a voltage, that's what they're telling you. Hook those 2 points to a battery. So let's find the current in each resistor, which means we need I1, I2, and I3. This is really, really simple. What do you think we do first? Notice how part A says find the current in each resistor. Part B says find the equivalent resistance. Are those out of order? Are A and B out of order? Should B technically be first? Can I figure out A without B? Yes, I can. And that would give you I. It is. Do what? No, let's do part A first. Because they each have the same what? Delta V. Mm-hmm. 18 volts over your 3 ohms. Yep, 6 amps. I2. Well, the hard stuff is coming back. It's just nice to take a break in the middle because magnetics is coming. Oh, yeah.
So like on my homework, I just know this paper. I don't know, divide it all one. You know, like the I two and I, so I have to write double divided by one thing. Before I put in my numbers.
Since you asked, yes. That is literally not the opposite of what I just said.
Yes.
Yep. Yeah, let's bring back opposite day. You have no assignment this week. Oh, is it? It's like when someone says back in the day, that's always a Tuesday. It's just back in the day, it's a Tuesday. What is the equivalent resistance? Mm-hmm. Now that'll get you part of the way there. Mm-hmm. This should give you about. You notice how the unit is an inverse?
All right, I it back.
Yeah, because this sum here will get you 1 over the equivalent resistance. So
No, do you want me to write down this in between sentences, right?
Well, here's the deal. If you don't, you get it wrong. The whole problem's wrong. You get no other points because I don't know what you did. Yeah.
Um,
Well, close enough. It's rounding, but then you need to practice with your calculator.
so I will by now.
What I'm confused about is you're a junior and you still don't know how to use your calculator. Well, look, if it works for her, it's great. I still say like TIs are superior, but you know. Now, what does part C say? Check that the total current through the system is currents 1, 2, and 3 combined. Okay, so what is total current? Uh-huh. No, I mean you can. You don't have to since you have I and then you have I1, I2, I3. If you want to do that, that's perfectly fine. This gives you 11 amps. So the question is, does that equal I1 plus I2 plus I3? Mm-hmm. Yeah, how did you get 11-ish? 6 plus 3 plus 2, that's just numeral addition. 11-ish? 11-ish. That's like you're in the hospital and it's like, did you draw their blood? Well, I hit the vein-ish. Yes.
Yes, to what?
There's not one that's more accurate than another. Yeah, you're just proving that these two are equivalent.
Well, I learned one, mine was on YouTube, but not, this one. 18 divided by 1.6 for reasons. 18 divided by 1.6 for reasons. 368.
Okay, go back to chemistry when we were doing molecular formulas, and you get your multiplier. Remember how you get a multiplier of like 1.99999? That's
So she's saying that. He's getting more close to the exact rounding. I don't know, I just want to know.
no. There's not supposed to be.
So 11. I don't know.
Are you back on the 11-ish? Yeah, that's 3. No, because this is an addition. This is not a multiplication. This is an addition. You round to the lowest number of decimal places. Yeah, if you were doing multiplication, you'd have to round this to 11 because those others are two significant figures. You round to the smallest number of decimal places. Round to the lowest number of sig figs. Okay. Is that something for the MCAT? All right. So EMFs in parallel. So if you have this, the equivalent EMF of your circuit is just going to equal the EMF of each battery. The reason this is usually done is putting batteries in parallel. You're going to reduce the internal resistance of your batteries overall and increase current to the circuit. You do not want to place batteries in there that are opposite polarity. But now, if you place two batteries in parallel that have different EMFs or that are reversed in polarity, you're not even going to run your circuit. You're just going to drain your batteries. They're going to compete against each other, and they're just going to kill each other. Putting two batteries together with different EMFs is like having a beta fish and going, he looks lonely, let me get him a friend. Yeah. I've been finding some really good ones about job interviews. I saw a meme that said the guy at the job interview goes, "My biggest weakness is honesty." And the guy goes, "I don't think honesty is a weakness." He goes, "I don't really give a crap what you think." It's,
You just showed it.
yeah. So okay, let's look at capacitors in parallel. So we just did resistors in parallel, and that was the 1 over Req. Now capacitors in parallel, you just have the CEQ is adding together all the capacitors. And once again, they're in parallel, so they share the same delta V. Now, as you notice, they all have different charges. So your total charge will be all three of those added together, which means that now Q1, C1 delta V, Q2, C2 delta V, Q3, and C3 delta V. Your total charge is your equivalent capacitor, delta V. And so and we can divide out the delta V's. It doesn't matter what the circuit element is. If it's in parallel, they all have the same delta V. Well, because now, and I want you to pay attention. This is one way you can draw a circuit. The next time so I'm going to show you another way to draw circuits. You can actually see. Let's go back up. I'll show you. You can actually see. Look at these resistors in parallel. Do you see how the main wire, the main wiring of the circuit hits this as a single unit? That means the delta V across that entire element, which consists of three resistors, is going to be the delta V of the battery. So they all share that delta V. So I wanted you to see this kind of notation too, because sometimes you'll see books draw them this way. This is you're gonna, in a second, when you see another way to draw this, just like I drew the resistors, they mean the same thing. So in parallel, your capacitors is 1 plus 2 plus 3, so on and so forth. Your resistors is 1 over R1, 1 over R2. So again, we're seeing how the capacitor and resistance equations are basically the inverse of each other. Now, here's another way you can draw capacitors in parallel. I do too. It's just good to know you can see it both ways. This one actually shows you the 4 capacitors as a single element in the circuit, and shows you that across that from here to here, they share a single delta V. So determine the capacitance of a single capacitor that is equivalent to the parallel combination. We'll call today after part A. You can, but since everything is a microfarad in this case, I can go ahead and leave them that way, and I'm going to get microfarads. Otherwise, you would get something like 4.5 times 10 to the negative 5th farads, which you just adjust to 45 microfarads. If you had converted these, if you had converted to that, and you added them all together, what you would have gotten that. But you didn't just move that decimal place one place to the right, and you're back to microfarads. If you're ever confused, just convert to SI units and you'll end up in the right place.
Here's my question.